What? I just want to make some analogies, parallels, analogies. And I'll start with a single integral with a silly example. So if my integrand was equal to 1, and I was to integrate this is just going to be b minus a. Is that correct? And we can think about this as simply the length of this interval. Okay? Now, geometrically, we think about the integral as being the area under the curve. And so we think about it as an area. But if the curve that we're talking about is a constant 1, and we're looking for the area underneath that constant curve, and we get an area, but numerically we're looking at the length. Right? Does that make sense? I mean, it's a silly example to say if I want to find the length from A to B, I would take the integral. You wouldn't do that. You would just say b minus a and then be done with it. But this idea got carried over to our double integral, if you notice. That if we took the double integral of 1, then we found that this is equal to the area of whatever domain that we took the integral over, right? And remember, there was a drawing for that. If we take a look at the domain D, and then a double integral usually finds us a volume of something, volume under a surface. But if the surface is just the plane z is equal to 1, then that volume is numerically equivalent to or is exactly equal to the area, except the one dimension higher business. Okay? So if we take this idea, a higher dimension, we have a simple formula for the volume. Well, simple, whatever that means. So if we take a triple integral and then we put 1 in the integrand, this is simply going to be the volume of whatever you're integrating over. So imagine your solid. This is a solid, whatever thing this might look like. It could look like a tetrahedron, it could look like a cylinder, a sphere, a cone, a solid. Solid though. There's stuff inside, not just a surface. This solid has a volume, and then we're integrating 1, so we're extending it to another dimension, but we're only going to multiply it by 1 unit in the 4th dimension, which numerically will be exactly the same as the volume because we just multiplied it by 1. So if you put on your 4-dimensional glasses, you can imagine this thing going out another unit. A 4-dimensional plane, W is equal to 1. Can you see it? You don't have your 4-dimensional glasses on. You might need some chemical help. Joe?
Why is it a solid and not hollow?
Because when we're doing a triple integral, we're looking at a solid, a whole solid inside. So when we're looking at a single integral, actually, I wanted to rewrite the single integral as an interval, because we're really integrating over some objects. Now, in one dimension, a one-dimensional object, as in for the single integral, we're integrating over a one-dimensional object, which is a line. In 2 dimensions, we're integrating, in double integrals, we're integrating over a 2-dimensional object, which is an area, a region. And so in 3 dimensions, or triple integrals, we're integrating over a 3-dimensional object, which is the whole solid. If you look at a surface is really a 2-dimensional region that has been taken up to the 3rd dimension and moved around. So imagine like a piece of flat rubber, like a paper, and then you put it up in 3 dimensions and curve it a little bit. So when you do that, then it's still a 2-dimensional object, but it's up in space. It's curved. But in 3 dimensions, when we're integrating over something in 3 dimensions, then we want it to be a whole solid. So a 3D solid, area in 2 dimensions, and then a line segment, let's just call it an interval. Which is a 1-dimensional object. So that's how we're going to deal with these integrals. We're going to integrate over the appropriate geometry, whether that would be a 1-dimensional interval or a 2-dimensional area or a 3-dimensional solid. And so what you're getting, if your integrand was equal to 1, you're either getting a length, an area, or a volume. Okay? Now, if you put something else in these integrals, then you're looking for something else. Could be looking for area, could be looking for volume, could be looking for a 4-dimensional hypervolume. Yes? Usually we just say hypervolume for anything higher than 3 dimensions. So it's a 4-dimensional hypervolume, and if you're in the 5th dimension, you can call it a 5th-dimensional hypervolume. I suppose you can say hypervolume, but what? It would be doubly redundant. Redundant. Okay, so when you see these triple integral problems, a lot of those problems are saying find the volume of the solid, and you just do a triple integral. Yeah, bounded by this, that, and the other thing. So let's do one of those problems to see if we can find a problem like that in this section. They don't have any Let's see if we can find one for my notes. I think the one we did was a tetrahedron one. The tetrahedron one that we did was actually a volume problem. So let's do one of these guys now. Maybe number 21 or 22? 22? All right, this will be fun. So the other important part in doing these problems is to be able to know your surfaces and these equations. Like when somebody says y is equal to -1, you got to know that's a plane. That's a plane, parallel to the xz plane. When you see a cylinder, this is x squared plus z squared. Now x squared plus y squared goes up along the z, so x squared plus z squared must go along the y. So those are certain things that you really have to pick up on, and you can only really get used to that by doing a bunch of these problems. So there are problems in the homework, but look at the problems in the examples also, because in the examples you can walk through them and you can see the figures, and then try some of these other problems in the exercises in the book, just so you can visualize them. And then a really good graphing program would be useful. The graphing program that's available free for you, the link that I gave you guys, is a good program, but it's harder to look at implicit surfaces. They have a special command for that, but if you have time to go to the Learning Center, all the computers in the Learning Center have graphing calculator installed, and so you can just type in an equation and then you'll actually see the surfaces. All right, so let's see if we can attempt to draw this. Because that'll give us an idea of how to approach this, if you can draw this out. So we're looking for a volume. Of the solid enclosed by the cylinder, and then you have a couple of planes. By the way, this plane doesn't have an x in it, so I would probably want to draw this on the YZ plane and then move it like a cylinder. Move it along the x-axis. So, drawing. Let's start with the cylinder. X plus z is equal to x squared plus z squared is equal to 4. So it looks like it's going to be a radius 2, and it'll be going along the y-axis. So I would draw it on the xz plane. I draw some circle in xz plane and then move it along the y-axis. And then I'll just do a rough sketch for now, and then eventually we'll refine it so that we can make it look appropriate, and you can get a better idea of how this thing would eventually look like. The plane y is equal to -1, so this is the y-axis, and then -1 would be over here, so that's going to get cut off right here. And then yz is equal to 4. Let's see, yz is equal to 4. I think that's going to be, wait, that's radius is 2. So yz is equal to 4. I would draw on the yz axis, purple, this line, which is, if I solve for z is equal to 4 minus y. So it will have a y-intersect at 4, and then it'll have a y-intersect, or a z-intersect and a y-intercept at 4, and then it'll be going down like this. And then it'll sweep across the x, or along the x-axis. So it looks like this thing might have gotten cut over there.
Y is -1.
The plane.
The domain of Y is
Okay.
-1 to the domain of Z is positive square root of 4 minus x squared, or negative square root of 4 minus x squared, positive third.
Okay, we'll get there. So if we kind of put all this together and take all the rest of the noise out, this looks like it might be the solid that we're looking for. Okay. All right, now there's a more appropriate order of integration here that would get us through to help us find this this volume. Yeah, so like Evan already gave us the limits, but you probably want to integrate with respect to y first. The idea is that if you would draw a line parallel to either the x, y, or the z, you want it to hit the same function all the way through. And so if you draw a line parallel to the y-axis, maybe I'll draw it a little bit higher over here, you'll see that wherever you draw this through, it's going to always hit a y equals -1 plane, the green plane, and then it'll hit this plane, which I want in terms of y. And as long as you stay within that disk, you're always going to be hitting these, going into the region and getting out of the region. So those would be a good set of limits for your y. So now that you've done the three-dimensional picture, it was difficult, right? And so now that you've done a three-dimensional picture, what you want to do is you want to rotate this and take a look at it without the y-axis anymore, because that's what we integrated with respect to first. So we have the x and a z, and then what you have left in the x and a z is a circle of radius 2. And then from there, you can integrate with respect to whichever variable first you want. And so I can decide to integrate with respect to z first. And then I would have to solve for that x squared plus z squared is equal to 4 business to get the positive and negative parts of the circle. So if I do z, I would enter this disk region with a z is equal to negative square root of 4 minus x squared. And then get out of this with the positive part of that. And then I got one more variable to go. This is going to be from what to what, where to where. -2 to 2, always constants. Okay? You probably could use polar coordinates. But the polar coordinate transformation here would not be, I probably wouldn't suggest it, at least not until we go into the next section. Probably wouldn't suggest it until we go through the first integral, the inner integral. Okay? Yeah. Yep. So let's do our triple integral. Our integrand is going to be what? Our integrand is going to be what? 1. We're finding the volume. Oops. We're finding the volume, right? So your integrand is 1. Now we're deciding to do our dv. We're deciding to integrate this in this order, dy first. We're going to integrate with respect to y. Our limits are going to be from 1 to 4 minus z. And then our x, or a z, sorry, dz from minus square root of 4 minus x squared to positive 4 minus x squared. And then finally our dx goes from -2 to 2. All right, so in terms of changing this to polar, I would be careful to make sure I do the inner integral first, which is fairly easy, right? The integrand of 1 is just going to be y with respect to y, and you put this and this into it. So this is going to be y, where y goes from -1 to 4 minus z, and so that's going to be 4 minus z minus -1, or 5 minus z. So I'm going to rewrite this, 4 minus x squared. Now, at this point, if you want to go into polar coordinates, we have to be kind of specific about your x and your y and your r and your theta, or in this case it's x and z and then r and theta. So we know that this region is a disk, right? And so we just have to make a choice as to which is your x and which is your y. So your x, I guess we can let your x be x, and then your y is going to be z. So x equals r cosine theta, y equals r sine theta. Let me change the y into a z, because those are the variables we have, and that's going to replace this z over here. So with the polar coordinate transformation, this is now just going to become r goes from where to where? Let me rewrite this first. R sine theta, and then don't forget the extra r that comes out of the transformation. The dr, r goes from what again? 0 to 2, because that's the radius. and then theta goes from 0 to 2 pi. Okay, now we have constant limits, but we can't take an r out. So we can't split this up to two different integrals. You see how there's a 5 here and there's an r here. You can't take the r out, so we have to work within here. We can multiply the r through, so let's do this integral from 0 to 5, 0 to 2, sorry. 5r minus r squared sine theta dr. I'll integrate that. This is going to be 5r over 2, 5r squared over 2, minus r cubed over 3 sine theta when r goes from 0 to 2. So it looks like 0 would go away, 2, this would be 4, cancel, this is 10 minus, this is 8/3 sine b, sine theta, sorry. And then now let's integrate from 0 to 2 pi d theta. This page is getting long. 10 theta minus 8/3. Derivative of sine is cosine. Negative? Negative, right? The integral sine is negative cosine. So let's put a plus there. 0 to 2 pi. So this will be 20 pi plus something that cancels out. And then 0. So I think we can stop there. Okay. Any questions? We kind of had to take that to polar coordinates. So the volume of this is about 20, or it's not about, it's exactly 20 pi, I guess. All right. So aside from the volume, this thing also has physics and engineering applications. So I'll put this big mess over here. There's a lot to look at, a lot to copy. Good thing the notes are going to be online so you don't have to copy it. We have the mass, just a triple integral. We have the moments. Now they call it the moment about the xy plane or the yz plane, and that's the one with an x in it. The moments between about the zx plane that has a y in it, and the moment about the xy plane that has a z in it. And these things would be numerators over the mass if you're looking for the center of mass. And so, by the way, the center of mass is called the centroid. And the center of mass, in terms of the balancing point, doesn't really make much sense in 3 dimensions because you're pretending to balance it in 3 dimensions, but physically that doesn't make sense. But in any case, that's the center of mass of a solid. And some of the center of mass problems that you guys might run into are fairly symmetric, like a cylinder or even a parabola. There's a symmetry in, depending on the function, there might be a symmetry in the shape. And so there's some of those problems where you don't actually have to compute one of the integrals because it'll be clear where the center is. And then the moments of inertia. And if you look at the formulas of the moments of inertia about an axis, like spinning about an axis, you can just see if it's spinning about the x, then the x is not there. It's just y squared plus z squared. So. And then I saw this electrical charge density in the book also, so I just wrote it down. So, it's like you could think about it as about the plane as going along the x-axis kind of thing, but we don't call the first moment as something that's going along the x-axis. So the YZ plane, for example, let's take a look at this one since it's easier to look at. So this is about the XY plane, which is to say, I don't really know much about moments. The way I think about moments is, no, well, they call it about the plane because the moments of inertia is about an axis. It looks like it's spinning about an axis. But the first moment talks about some sort of symmetry about like this one, about the XY plane. And what that does is it helps find the average along the z-axis. And so what this kind of gives you is it kind of gives you, if you have a solid, let's do a cylinder, for example. And let's say the cylinder is, the density of the cylinder is evenly distributed. So we don't have to do any integrals. When we're looking at the moment about the XY plane, we're looking at more or less the average that this has that's parallel to the XY plane. And so the average that it has, I guess the idea is that if you cut it with a plane that's parallel to the XY plane, then that's going to be the center of it, kind of. I don't know. Talk to a physics teacher. That's kind of like how I see it, but I don't know how accurate that is. The inertia makes a little bit more sense to me because it spins around an axis, so that seems to make more sense. But this idea of center of mass kind of tells you that if you're looking for the center of mass, the x component of the center of mass, then you're essentially finding the average value within the center of mass along the x. And so they say here MYZ, which is the moment on the YZ plane, about the YZ plane, and then you have the x variable in there. I don't know if it's pushed along that plane or pushed perpendicular to that plane. I think it's more perpendicular to that plane, which is essentially along the x-axis or the z-axis. Yeah. Okay. We could do one of these problems, but it's just, again, it's just plugging into the formula. So we'll take a look at it. Maybe we might go a bit of the way, but not all the way finish it. Looks like the last problem, your triple integrals homework might have something like that. So let's take a look at doing one of those guys. It says find the mass and center of mass of the solid E with a given density function. So E is lies under the plane. It's a solid, so there's a plane, the region in the XY plane bounded by the curves, and your density function is constant 8. So that makes it a little bit nice. So what we have to do is we need to focus on your plane and these other things. So I don't know if, as long as the plane doesn't have a d constant that's 0, then I think this is something we can kind of draw out. But if d was equal to 0, then it'll be more difficult to draw because the plane will actually pass through the origin. If it doesn't pass through the origin, then it's going to have to hit the axis at 3 different places, which is kind of nice. Nice for us to try to capture. And so we could try to draw this as intersections on the x, y, z axes, just like we did last time. So let's find the x, y, z intercepts of this. So this thing's going to intersect the z-axis when x and y are equal to 0, right? So if you set x, y equal to 0, you get z is equal to 3. And then if you set 2 others equal to 0, set maybe x and z equal to 0. And y equals, negative 3. So y equals negative 3. And then it looks like x is also going to equal negative 3. So this is not in the first quadrant or octant. That's too bad. Makes it harder to draw. Oops. Anyways, that didn't work out so well. So the plane is going to have to extend. This is just a portion of the plane in the, let's see, first, second, third octant, I think, if you're counting the octants. Yeah. Octant is how the, quadrants is split up to 4 equal quadrants. Octant has 8 because there's 8 spaces that's split up. If you have each of the coordinate planes splits up the space into 8 spaces. Anyways, that's not a good way to attempt to draw that. But let's just move on and see if we can draw the other curves here. Now, on the xy plane, bounded by the curves y is equal to square root of x. Now, you kind of have to draw this. You may have to draw this on a regular xy plane first and then see if you can transfer it to the 3 dimensions. So y is equal to square root of x. I think it's a square root function. It's like a sideways parabola. Y is equal to 0. That's the x-axis. And x is equal to 1. So you can see where your actual region is. And so you can kind of see that region over here if you try to draw it. So imagine that the plane that I drew would be extending, and then so you can just imagine that this is probably going to go, I don't know, just making it up now. Something like that. Kind of, yeah. Let's see if we could draw this a little bit better. So this is the side. I would imagine that that plane is kind of steep. Boy, I don't know. I don't know if that worked any better. Anyways, so you have this thing, this solid, and what's important about the solid is that you have you have vertical walls on the solid, and so the vertical walls, vertical going along the z-axis, would help us probably want to integrate with respect to z first. If we integrate with respect to z first, we'll see that we would be going through the xy plane, z is equal to 0 on the bottom, and then we're going to be inside of the region until we hit this top plane, the plane that they gave us over here, z is equal to 3 plus x plus y. And then that'll take care of our z component, and then we can just focus on the xy plane to take a look at the other two limits. Okay? So given that idea, we got our z limits going from 0 to 3 plus x plus y. And then now our x and y, we can just do that here. And in this case, we can either integrate with respect to x first, or we can integrate with respect to y first. Now, which one would be better to integrate with respect to first? We could do it either way, but one of them is slightly easier than the other. Which one? And why? So we want to integrate with respect to x first or with respect to y first? Why? I meant W-H-Y. Why? Why? Y is correct, but I want to know why. Yes, because one of your limits is equal to 0. Okay? So that's why we would want to choose y. Because if we go, let me take out the x, just so we don't confuse ourselves. If you integrate with respect to y, you got y equals 0 as one of your limits, and we always want to try to have zeros in the limits and make things easier if you were asked to actually compute the integral. And then we'll be inside of the region, and then we'll get off of this function y is equal to square root of x. So those are our limits for the y. If you'd done the x first, we would hit this curve, x is equal to y squared, and then x is equal to 1, which are valid limits, and you can do it, except if you have a choice of having a 0 as one of your limits, then I'd probably go with that. If it was a choice. If it wasn't a choice, then you just have to do what you got to do. So we got y to square root of x as our y limit, and then our x goes from where to where? Constants goes 0 to 1. There you go. Okay? So our mass is going to be our triple integral, and our function is a nice constant 8, which we could take out if we wanted to. We're going to integrate with respect to z first, from 0 to 3 plus x plus y. And notice that z has to come first because the z function depends on x and y. And so we need to take care of those integrals. And you can't just switch integrals around if you don't have constant limits. We know that. dy goes from 0 to square root of x, and then finally our x goes from 0 to 1. Okay? Now, I won't go through this, but the next thing that we want to find x bar is to find the moments. So we have 3 moments to find, and they're essentially going to be set up the same way. It's a triple integral, but this time we throw an x in there. So it's still going to go from 0 to 3 plus x plus y in the z, and then in the y it's going to go from 0 to the square root of x, and then the x is going to go from 0 to 1. And whatever you get there, your x bar is going to be this answer to the second integral divided by the answer to the first integral, which is the mass. Okay? Any questions? It's driving you crazy? Now, the graphing calculator might help us visualize this a little bit, but we won't get a feel for the exact area or the exact solid, because it's hard to trim this. And that could be some interesting extra credit problems for you guys to try to look at volumes and trim it around so that you can get the whole solid. But if we graph this, z is equal to 3 plus x plus y, and then what are the other graphs? X equals 1, y equals square root of x. And the xy plane. So if you can somehow peek where that area is, it's in there somewhere. I don't know if this will help, but we can make all this transparent. Yeah, the space bound by this. And if you zoom out enough, you can see it. Oops, zoom out. You can see it getting closed. You see it? No, I don't see it. It's in there somewhere. So a good exercise is for you to try to trim this down and see where that area is. Oh, there was another. I'm missing a plane, aren't I? Oh, it's right here. It's really small. Anyways, I could take a look at that and see if I can trim it down so we can take a closer look at it. But I'm not going to do it now. All right. Any questions? I had some ideas for extra credit, and these extra credit problems are really directed towards people who need extra credit, and usually when I give extra credit problems, people who don't need extra credit are the ones that do them, and people who need them say, I forgot to do it, I didn't do it. And so I would highly encourage people who need extra credit to do these, and the people who don't need extra credit to not do them. because then that's more stuff that I have to look at. I mean, I don't want to do extra credit because I have to look at them and I have to find solutions to them so I can check my work with your work and stuff. But there are people that need them. And I think by doing these extra credit problems, it would not only give you extra points. I mean, that extra points is really the minor result of extra credit. I think the bigger takeaway for you doing the extra credit would be being able to do these problems that are not easy. And if you can tackle these problems that are a little bit more difficult than what you would expect on the exam, then that could kind of give you a little bit of confidence to do a little bit better on the exams. So that's the general idea behind some of these extra credit problems. And so I was able to find 3 based on what we've done so far, and there's a couple of other cool ones that I want you to look at, but they're not going to be available until next week because we haven't gone over the last 3 topics. So, extra credit stuff. I guess I could just type this up. And these are just from the book. So section 15.4, number 40. Number 40 in the book is kind of an extension to that e to the negative x squared problem that we did. It actually, the first 4 parts is essentially that. And then the last couple of parts extended to you're actually looking at the standard normal distribution. And so there might be, Trevor came up to me after class yesterday, there might be some issue with a substitution. So I'd ask you to, if you're looking at this particular extra credit problem, to look at the substitution that they suggest. And it may work, it may not work. You might have to do your own substitution because it might be done incorrectly, presented incorrectly in the book. Number 29. So this one is an application to probability. The one we did was a nice square probability, I think. It was nice and enclosed. This one is one of those that goes off to infinity. So it'd be nice to explore one of those exponential infinity problems. And you want to show that it's a density function. You want to find some probabilities within the areas of these things. So these are all manageable. And this last one is finding the surface area of an intersection between 2 cylinders. Next week, we're going to find the volume between 2 cylinders. So we'll extend this idea to volumes for next week. All right, yeah. Monday. So remember, those people that need extra credit, do them. Come on, you want to come in? Oh. Mind trouble? Okay.